So if you recall what we had covered last week, we had gone through the internals of how Java 8 parallel streams was implemented. So we went through all the details of how things worked. Also, no laptops, please. So what we'll do now is we're going to talk about how to go revisit the previous sequential stream solution and modify it with parallel stream support. And we're going to go one step further here and illustrate how to take the parallel streams version. Remember, the parallel streams version had that couple of little minuscule tweaks. This version is going to go one step further and make it even cooler by adding a parallel spliterator. So this parallel spliterator version is going to further improve the performance of this particular implementation by having yet another thing run in parallel. And as you'll see, when we run the results, this version, the one that we're looking at now, the parallel spliterator version, is the fastest of all the different approaches that are done with the SearchWithStreamGang example. And it's even faster than the one we looked at before that was the parallel streams approach. So we'll take a look and see how that all works. There's a whole pile of different implementations of SearchStream examples in this app. And this is the one that is the most aggressive. It's called SearchWithParallelSpliterator. And it does 3 levels of parallel processing. So first, each chunk of input is searched in parallel. So, each work of Shakespeare, we have each work of Shakespeare running in parallel. We have the chunks of the phrases being searched in parallel on a given input string, on a given work of Shakespeare. So all the phrases are being worked in parallel, searched in parallel. And then finally, we're searching chunks of each input string in parallel. So it's not just that a single string is being searched, each string is being searched in a different core. Chunks of each string are being searched in parallel. So it's really by far the most aggressive parallel strategy that we've looked at so far. So we're searching things in 3 different dimensions. And I actually wrote a little program to illustrate how all this works. This is called SearchStreamSpliterator. It's just a variant of one of the SearchStream examples here. And what we do here is I actually try every possible combination of parallel versus sequential for strings, phrases, and chunks of input strings. And so you can see here there's 8 different combinations. And this then takes a look. This runs for each work of Shakespeare. It shows all the different combinations and how they perform. So not surprisingly, the version that is sequential for all 3 of these things takes the slowest time to run. It takes about 3,000 milliseconds. And the version that uses everything in parallel runs much faster. So you can see it's a lot faster. And it's the fastest. So all parallel is the fastest. All sequential, no surprise, is the slowest. And then some interesting combination of everything else fills in between those things. Just for kicks, I ran this with a different approach to the works of Shakespeare. I wrote a version of the program that splits the works of Shakespeare up into 2 chunks. The first half of the works of Shakespeare and the second half of the works of Shakespeare. So that meant that each of the 2 strings were really long, whereas the previous version, I'd had each string be whatever the number of characters were in the works of Shakespeare. So in this approach, it was 2 strings. So each string was much bigger. And you can see that this ran a little faster. And that's because we were able to leverage parallel processing of chunks more effectively in this particular approach. So here's where this actually gets used. If you recall, there's a process input method. Remember, there's process stream and process input. And process input is the one that takes an input sequence, like a work of Shakespeare, like Hamlet, and then it goes ahead and it searches for all the phrases to find in parallel. And so you can see we have a parallel stream. And what we do here is we say, turn the phrases into a parallel stream. Then for each phrase, search the input Hamlet for that particular phrase and do all that in parallel. But what we're going to do here is, unlike the original version, which had a false value here, which said search that input single input string for each phrase in parallel. Now we're going to break up the input string and search for the phrase in the input string in parallel. So it's yet another degree of parallelism. And so putting a true here instead of a false will do something really important. And what it's going to do is shown by the search for phrase method. So here's search for phrase. And what this does is it takes a phrase, an input string, a title, and this flag, and it goes ahead and makes a spliterator, which will split up the input and associate it with the phrase that we're searching for, except what we're going to do this time is we're going to pass a value of true to the parallel final parameter to search for phrase. So we'll pass true here instead of false. And what that does is that says, go ahead and create a parallel stream to search the input string in chunks in parallel. So by putting a true here, it's going to say, stream support, go ahead and do parallel processing as opposed to sequential processing. Before we had sequential processing, now we're doing parallel processing for all this stuff. So the magic here is you just change one flag from true to false, and things are going to run faster. The catch, of course, is now we have to implement a parallel spliterator. Before we did a sequential, before I only showed you a sequential spliterator. And if you recall, the sequential spliterator just had to implement the try advance method, and everything ran in one thread of control. So now we're going to do the parallel spliterator instead. The cool part is that all this stuff lives in a single class. So the phrase match spliterator class works for both sequential and parallel streams. Earlier I showed you the sequential version. That's the one that used try advance. Now we're going to look at the parallel version, which is going to use try split. And the purpose of this is to further optimize the performance. You'll see that if we didn't get a performance win, this wouldn't be worth it, because it's a lot of work to implement this particular parallel spliterator, as I'll show you in a second. Okay, so here's kind of the context in which this occurs. Here's the big picture. So remember, we've got actually that should say parallel stream, not stream. This is a parallel stream, and then along the way here, because it's a parallel stream, these things are going to run in parallel. And then along the way, for each input string, we're also going to search for that in parallel as well. And that's what gets done when we're transforming a stream of strings to a stream of search results. Here's the big picture view, and then we'll dive into the code. But first, you have to kind of understand it at a high level. Let's imagine we have a given work of Shakespeare, like Hamlet. And so we want to search for a phrase, and we want to see if we can find it in there. So what the spliterator is going to do is it's going to split the input string up into multiple chunks. So let's assume, for sake of argument, we're searching for brevity is the soul of wit. That's the phrase we want to look for. So the way this is going to work is that the phrase match spliterator, when run in parallel mode, is going to break the work up into chunks, and then it'll search each chunk in parallel. It'll search for the phrase we're looking for in each chunk in parallel. So let's say, for sake of argument, that we split it in half. And let's say, for sake of argument, that that's where it's split. So this will get searched in one thread, and this will get searched in another thread, and those threads are going to run in parallel. Whereas before, if we'd done it without using a parallel spliterator, it would have searched for the phrase in the entire string in one thread. Now it's going to use parallelism to search for the phrase in multiple threads. And if you can do the splits evenly and efficiently, then we'll get a big speed up. Now, here's the tricky part. We have to be really careful how we go ahead and split the input up into chunks, because if we're not careful, we could split the input in such a way that the phrase we're searching for spans where we did the split. So if we were to split it this way, we would never actually find the phrase, because brevity is the soul of wit wouldn't be in this substring, and brevity is the soul of wit wouldn't be in this substring. And so if we search them in parallel, we wouldn't find them. So we have to make sure that when we do the split, we always split in a way that respects the phrase boundaries, because otherwise we won't find what we're looking for. Okay, so here's kind of how we're going to do this. We're going to have phrase match spliterator. I showed you this before. It implements the spliterator. It's got a whole bunch of methods that are defined here. And these fields we're about to look at implement the various semantics for both sequential and for the parallel use cases. So remember, the input is the work of Shakespeare, or the chunk of the work of Shakespeare we're searching. The phrase is the phrase we're looking for in that chunk. The pattern is the regular expression that corresponds to the phrase. The phrase matcher is the combination of the pattern with the input chunk. And then we've also got a couple of other fields, one of which is min split size, which is how much are we going to split this string and do it in parallel. And then m offset is used to keep track of where we're going to find the result in the string, even if it's split. And as you'll see in a second, the try split method actually will update some of these fields, which is why we don't make them final, all of them final. Here is the regular expression, or a portion of the regular expression that we used for the input phrase in the phrase match spliterator. And as you can see, it's very complicated. And so we compile that regular expression into a pattern that can match phrases across lines. That's what .all means. We do it in a case-insensitive way. And then we associate the input chunk with the pattern matcher to make the phrase matcher. And then we also keep track of like the min split size. Yes?
Does this mean that the min split size is hard-coded?
We hard-coded this. Basically, this will take the input string and chunk it up into four units. So it'll take its length, divide it by half. And the reason for doing that really just has to do with there's a diminishing returns. If you chunk the strings up into very small pieces, it takes a while to chunk them up, and you don't get much of a win from searching in parallel. So it's kind of a trade-off.
When you tried it with 38, you had to come in.
Exactly. Yes.
So is there like a, so when you say diminishing, how do you find the whole number of?
Yeah, that's a great question. So, I mean, if you really cared, you'd spend some time writing a program to experiment with different things to train your input. It's like, supervised machine learning. You train it so it would know kind of what the best result was, or you just approximate. If you notice what they do with Java 8 collections, the class libraries and the way that splitterators work in the Java 8 collections, they typically split just down to a size of element of 1, which in this case would be crazy because we're looking for phrases which could be long, so it doesn't make sense to split your input string up into, character level stuff. It would never find the phrases. So you could be smarter. You could take into account how big the phrase was and use that to indicate how to chunk up the split size if you wanted to. Here's try advance. So remember, this is used by the streams framework to iterate through the results. We take an action, which is going to be used to pass the results back to the stream framework. We use the find method on the phrase matcher in order to see, does this phrase occur in the input string anymore or at all? And if it doesn't occur, or we've already found all the occurrences, then it returns false, which tells the streams framework, stop processing this thing, you're done. Yeah?
Does this work if, so let's say we split the input string.
Yeah.
What if the phrase, split by that split? So, what if it begins the first half?
So remember, I mentioned that over here. I was telling you how we have to be careful how we always split things. So if you're careless and you split things like this, then you wouldn't find it. You'll see in a second, our spliterator is going to be really smart to do the splitting properly. So we're not going to split across phrases. But that's a good question. So if we're all done, if there's no more matches, we're finished. Otherwise, we go ahead and figure out where the match occurred. We store that into a new result object, which just keeps track of the index, where it occurred, plus the offset. And then we go ahead and accept this. So that'll allow us to pass it back to the streams framework, indicating where the match occurred. And then we'll return true, which says, hey, we had a find, we found one, try again. Okay, try advance gets called sequentially. So when you've reached a point where you're not going to split up the input any further, then try advance is called in order to be able to consume it. Try split, however, is what's used to actually break up the input string into its chunks. And this comes back to what we were just discussing about doing a very clever way of doing the splits. So try split is actually a method inherited from spliterator, and then we added some other helper methods because this code is complicated, as you'll see in a second. As always, there's no locks in this particular approach. We don't need to have locks. And remember, this is the way that try split works. So the goal is to try to split things evenly. But as we'll see, we don't have to split it 100% evenly. In fact, if we tried to split it 100% evenly, that's where we would run the risk of splitting the input across the phrases so that they wouldn't actually be found. So we're going to split it as evenly as we can while still not splitting across the phrases. So here's what the code looks like. This is try split. And you can see try split calls compute start pause, try to update split pause, and split input. Those are some helper methods that it's going to use. The code itself, if you go read it, is very heavily commented. I'll walk you through the high order pieces here. All right. So the first thing we do is we check to see, is the size of our input less than the min split size? If it is, we're going to bail out because we're not going to split it down to infinitesimally small chunks. We want to keep it pretty sensible. And you'll notice it returns null, which is an indication to the streams framework to start calling the underlying try advance method to get through the rest of the string in sequentially. We then take a guess at what the split position should be. And you'll notice up here, just to make it more clear, I have a little excerpt of the input string, which starts somewhere over to the left and continues off to the right somewhere. And let's say just for sake of argument, the splitting in half was going to cause the string to split across the phrase we were searching for, which would be the bad thing we were just talking about. So that's our initial guess. So we guessed wrong, but that was our starting point. The next thing we're going to do is we're going to call this method called compute start pause. And it's going to guess where the search should start. So what does it mean for the search to start? Well, let's say for sake of argument we split it in half, we need to start searching at a point that makes sense given the length of the phrase that we're looking for. So we have to actually go back into the left-hand split and figure out where we need to start searching in order to possibly find a match. Wouldn't make sense to start searching, here because it could never possibly match. So we have to go back far enough based on how big the phrase is. So we start out by figuring out the start position. And here's what this does. It identifies the position to start determining if a phrase spans the split position. So we figure out the length of the phrase, which is, the length of brevity is the soul of wit. Then we go ahead and take the split pause and subtract the phrase length, and that gives us the start pause. And then we check to see whether or not this is a sensible range, if it's too long for the segment, in which case we fail. Otherwise, we return our candidate start. This particular method does not take into account phrases spanning across the split. It just tries to figure out where we want the split to start. All right, so here is, now we've updated start pause, so that's over here. And now we're going to go ahead and update the split position. Remember before, that was our initial guess at where the split position should be. That's just length of the input divided by 2. But that was wrong because it would split the thing across a phrase. So what we're going to do now is we're going to call this method called try to update split pause, which will give us a new split pause that makes sure we don't split across the phrase. So we want to split here, not here, because this way we can actually get a match in at least one of the searches. So let's take a look at try to update split pause. So this is where we start. Here's start pause, and here's the original split pause. And of course, we don't want to split the string, we don't want to split the input string across a phrase. So the next thing we do is we figure out what the end pause is. So that's basically used to ensure the phrase isn't longer than the input string. So we just do, again, a little sanity check here, and we bail out if that isn't the right result. And then what we do is something really cool. We're going to go ahead and create a substring which is going to start at the start position and go to the end position. So anything within here is fair game. And now we're going to see whether or not the phrase that we're looking for is going to occur anywhere within that phrase. So we're going to go ahead and do a match to see if it's going to span it'll span the split. So that's what this is doing. Then we go ahead and we call find, and we see if there's a match. And if there is a match, then it means we have to update the split pause in order to be able to ensure that we don't split the string. So the new split pause goes here, which is the start of the match plus the length that mapped, so that'll get us the new split pause. And then we go ahead and return that. So the bottom line here is if there would have been if the split pause would have caused the phrase to be split across the chunks, we're going to move the split pause to the end of the chunk. Oh, sorry, to the end of the phrase. And so the new chunk will start after the end. Yeah? I'm sorry? I didn't understand the last part. Oh, in this particular case, we have in fact found one occurrence of the phrase, which was where we're trying to do the split. So we know that, but we're not going to use that. We're not going to take advantage of that. We're just trying to find out where to put the split. So now we would know. I mean, if you were really paying careful attention, you would know that there was in fact, if this particular if statement gets run, there is in fact a match, and we're just making sure that the rest of the searching won't miss that match. So we don't really take advantage of the fact that we found one match, because there could be lots of other matches in the chunks that were not split, where the split did not occur. Okay, so when we're all done with this, we've now got the input split up into two chunks, and we know that we know that if there is a match, the match will be found in the left-hand side. But what we're going to do now is we're going to take the split pause and we're going to make a new spliterator that'll have the left-hand side here going up to the end where the split needs to occur, and then the right-hand side will be the beginning. Now, obviously, if there's no match, then it'll just be the original split. It'll just be splitting it in half. So here's split input. This creates and returns a new spliterator. You can see what it does is it makes a left-hand side, which is the subsequence from 0 to the split pause, which is right here. Then we go ahead and update the right-hand side. We update ourselves to be everything from the split pause to the end of the string. So now we've got a left-hand side and a right-hand side, the right-hand side being ourselves. And then we go ahead and update our phrase matcher to indicate the new subsequence, which is just this part. That's what we're going to be searching for in the right-hand side. So we update this to be the right-hand portion. And then we make ourselves a new phrase match spliterator and return it, which will focus on the left-hand side. That's what LHS stands for, left-hand side. So we return a new phrase match spliterator, which will then look at the left-hand side. We update ourselves to be the right-hand side. And then both of those things, surprise, surprise, will run in parallel. Yes? It doesn't, well, if you want things to be ordered, it matters. But if you don't really care about order, it probably doesn't matter. But the most important thing is they're split in half. By convention, you typically have the left-hand side be returned as the new spliterator, and the right-hand side is just modifying this. That's kind of the convention that people follow with streams, and that helps to preserve the order a bit better. But it probably won't matter in general. Okay, so now that we've chunked these things up, they get thrown, these chunks of stuff get thrown into the fork join pool along with all the other chunks, and the underlying fork join pool does the parallel processing in order to be able to do all of this in parallel. So yet more stuff takes place, and that's why we have all the little brooms all off running in parallel, because we've got more things to do in parallel. All right, we'll talk in a second. We'll evaluate this and talk about the pros and cons of what we just did. But that's just an overview of the nuts and bolts of how it worked under the hood.